All right, so let me start then. Today we are here to share some of the experiences that we had in converting a production level CMS analysis to from a more traditional approach, let's say, to distributed RDataFrame. And this is going to be completely written in Python. You will see more details about that. So I will start. My name is Vincenzo Padulano, so I will just introduce the objectives of this joint effort between ROOT team and some of the guys from the INFN group. I will describe some of the features that were specifically developed within RDataFrame for this effort. And then I will give the floor to Tommaso to talk a little bit more in detail about the analysis facility that was set up to test the tools, some of the performance that we could measure. And then finally, we'll finish the talk with a demo of what we did. So let me just start by saying that this is an R&D project, a little less than a year. We've been trying to improve or at least research on some of the new approaches that we can use for data analysis. In this case, it's going to be specific for the CMS analysis, but all of the things that you hear today about the tools, the approaches can actually be quite generic, quite more generic. And although it's an R&D project, as I said, it is very much usable already today. So hopefully you'll be interested in trying it out, maybe on other hardware than what we have used and other analysis types. So the general idea, of course, is something that can be quite something that is quite natural. Let's say the continuous optimization and improvement of our workflows. And nowadays, and it will be even more so in the future, this means a very heterogeneous type of platforms, from single core or many core computers to many nodes in the same computing cluster. But we want to make the experience as easy or as streamlined as possible for the final analyst, from 1 core to 1,000 cores on different machines. From the user perspective, this usually means running an analysis on billions of events in CMS, and especially in this case, we are going to discuss the processing of nano-AD data format, but this is again quite generic. It used to be that one needed to submit thousands of single core jobs to the grid, and then resubmitting those jobs that were failing and then merging them. There were multiple steps involved in this workflow. We'd like to see some way to just streamline all of this in a tool that is interactive, and at the same time takes away all of those responsibilities from the users. And when we say interactive, what we actually mean is being able to use a simple interface, but with the full power of, in this case, a tier 2, so multiple machines that can still run the computations in a transparent way that is kind of decoupled from the actual interface or the machine where the analyst starts the analysis or writes the analysis. At the same time, we still recognize that the batch features, so the batch systems are there, and the resources that they can manage are totally necessary for this type of analysis. So it would also be very nice to finally have some infrastructure that is flexible enough to accommodate both the more interactive use cases and the more batch-like approaches. And this is one step towards that kind of approach in general. As far as the analysis tool is concerned, we think that distributed RDataFrame can be one such analysis tool that allows all of the requirements that I just described. And in particular, let me just give you a recap. RDataFrame itself is the main analysis interface that Root offers nowadays. It's been in production for a few years now, and its usage and description are out of scope for this presentation. So I will just move directly to saying that there is a distributed layer for RDataFrame, such that all of the responsibilities of creating the jobs, splitting the input data set into different chunks that are then processed by all jobs, and the merging of the results and sending the result back to the user, all of these features are integrated in a single Python layer that takes care of running the RDataFrame C++ event loops inside of the computing cluster. These can run currently with either the Spark or the Dask schedulers. And this means that within a single API, which you can see sort of sketched here on the right, you will see more details later, a user has access to multiple types of backends, both from the scheduling point of view and from the cluster management point of view. In particular, Dask is quite popular, has gained quite some popularity because it has very nice interaction with batch systems like Slurm or HTCondor. So that's also a very nice addition. Some of the things that were specifically developed for this effort in the distributed part are, for example, the fact that distributed RDataFrame jobs are flexible enough to understand whether a certain task will actually have to process some entries or not. In the cases a task doesn't need to process any entries because, for example, in the data pipeline, some of the input files for the analysis were previously skimmed and they led to empty files. Then the actual RDataFrame task becomes a no-op. So there will be no extra usage of resources on the cluster. The task will just stop. So only the tasks that actually have to do something will process the data set. And this was crucial also to, in general, as a distributed engine, this is crucial to have some flexibility in the kind of scheduling that you can drive to the computing cluster. Together with this, a whole lot of other RDataFrame operations were added to the distributed layer. Here I am listing them. There's define per sample, there's redefine. And then there are two, let's say, maybe more common or more important ones that are the systematic variations and the possibility to run multiple RDataFrames concurrently, distributedly in this case. So let me just say a few more things about those two. The latter one, it's called run graphs. You can see an example snippet here. The run graphs operation, which is already available with the traditional RDataFrame, means running multiple RDataFrames concurrently. In the distributed case, it means executing or launching the distributed tasks of two different RDataFrames that can process different operations on different files at the same time. So instead of launching only the jobs of one RDataFrame and then the jobs of the other one, you launch all the jobs together at the same time, and then the cluster scheduler will take care of running them within the resource limits. And finally, systematic variations, which were added to traditional RDataFrame in the last root release, have also been added in the distributed version for the purposes of this work, and they will thus be available in the next root release. In both cases, for the variations, systematic variations effort, and for the run graphs that I just described, one of the nice features of the distributed layer is that the API doesn't change at all. So you will be able to run your RDataFrame analysis as it is currently today, but in a distributed environment with no extra code change needed in that sense. Finally, just a final thing to say for the purposes of this study, we wanted to gather all the metrics possible about the resource usage. So now inside of the RDataFrame task, there are automatic logging. There is an automatic logging systems for metrics such as CPU, network, and memory, so that these can then be more precisely evaluated after the execution of the distributed graph. So with that said, I will just stop sharing my side of the screen, and then I will leave the floor to Tommaso for the rest of the presentation.
Thank you, Vincenzo. Can you see the slides? I think I am full screen now. Can you see? Can you confirm?
Yes, yes, I can see.
Okay, okay, thank you. Okay, so as Vincenzo said, I will talk about the actual infrastructure and the use case that we use to test this infrastructure, and the infrastructure served as a benchmark for this analysis. So first of all, the infrastructure, the INFN facility that has been built up is built upon three main building blocks. For the user, to manage the user-facing part, we use JupyterHub and JupyterLab. So the user access the JupyterHub and then works within a JupyterLab session. Then he can access the resources via Dask. So Dask introduces the scaling over a batch system, which in this case is HTCondor, and that access is provided via XRD protocol. Since at CMS and INFN, the topology of the resources is distributed and pledged, we try to integrate everything and possibly even opportunistic and private clusters as resources. But this is not a user issue. Basically, everything is hidden behind a single hub, and so the user doesn't have to worry about grid, the difference between running on grid resources, cloud resources, and so on. So in principle, the resource could be a cluster, a single fed node, a cluster of fed node, and so on. So this is the infrastructure that we used, and the use case that was mentioned before is a real VBS inside WW analysis with an hadronic tau and a light lepton in the final state. This analysis uses NanoD inputs, so which are CMS specific format that are basically plain root files. And this analysis was firstly implemented in with a legacy approach, so meaning using NanoD tools and PyROOT based scripts, and was ported then to distributed RDataFrame. The aim was to achieve enhanced user experience and improve the efficiency, and to optimize the workflow and the operations on data. As Vincenzo said, there was a continuous collaboration between the INFN group and the ROOT team in order to implement, to test and implement the RDataFrame features needed to streamline a full-scale physics analysis, and then to evaluate the performances. Talking about some details, this analysis is can be split into different parts. The first part is a part that in the legacy approach is run on CRAB, so on grid resources, using NanoD tools, which includes a scheming based on triggers and a first preselection of the objects, and then the computation of all the necessary corrections. The second part is run in the legacy approach on HTCondor at CERN at Helix Plus, and uses plain PyROOT scripts plus some utils from NanoD tools. And the event loop on events is run for each systematic variation. Then it comes the merging of the results and the histogramming. Those two parts were ported to distributed RDataFrame, and so they are both run on the INFN analysis facility. So using a Jupyter notebook basically, and so running on the resources that I mentioned before. And thanks to the advanced feature that Vincenzo mentioned before, the systematic variations and the merging steps are all done automatically in a single event loop. So here is how it looks, an analysis code in distributed RDataFrame. Basically, you have first an initialization function where you have to declare all your C++ function that do what you want in the analysis. Then you declare you define your RDataFrame with your distributed RDataFrame. And then you go with your analysis, so with a bunch of defines and filters. Finally, you save your results with a snapshot, or you get your histograms with a histo1d method, and you can also inspect the data using display. So the parting targeted these functions that are used in the analysis, which are, as I mentioned, the C++ function that manipulate RBAC objects. If you want to introduce the variations, it is trivial. You have only to insert the vary statement in the analysis, and then do the variation for command, and that's it. So we monitored the task execution. So thanks to all the features that were implemented, we were able to look at all the performances of the code, basically. So as an example, we took the pre-selection part, the pre-skimming part in a distributed RDataFrame, and then we can have a look at the CPU usage, the memory usage, and also we set up a monitoring for the network RED. In order to have control of everything, basically. Basically, we took as a benchmark the analysis of a part of the run to Monte Carlo that we use in the analysis. In particular, we use 1 year, the 2017 Monte Carlo Ultra Legacy, which is 1 terabyte worth. And basically, we looked at the increase in terms of speed up of the analysis, overall speed up in terms of time, and basically we are getting something of the order of 10 times what we achieved with the legacy approach. So in order to be concrete, we will see a short demo. I will show a short demo that shows how we access the analysis facility, how we set up the Dask cluster, and then how we run a notebook with analysis code. It will be a very simple example, but it's just for showing the workflow, let's say. So I will be very fast. So first of all, we have to go to the proper endpoint, basically, and log in with the CERN single sign-on. So once you logged in, you have to spawn your JupyterLab session. In this case, I will use my custom image. And everyone is free to use its own image and choose the resources to be deployed. So now the container is starting, and soon, in a matter of tens of seconds, we will be able to get access to the JupyterLab environment, to the JupyterLab session. And basically, we will first deploy the Dask cluster on the distributed resources. Then we will run the analysis and get the results. So we are automatically redirected to the JupyterLab. First, to deploy the Dask cluster, we have to go to the Dask extension and click on New. Here you can choose the resource the tier, the resource that you want to use to deploy this. Basically, you have to choose which HTCondor pool to use. In this case, we will use the tier 2 resources at Legnaro. So by clicking on Create, you basically are launching, submitting a Condor job to that HTCondor pool. In fact, if we look at the Condor queue, we will see that there's an idle job, and this idle job contains the Dask scheduler process. So as soon as it goes running, here it is, we will see here the connection starting. Here it is. And then we will be able to see the dashboard here with all the important tabs to see the status of the cluster. Here it is. So let's have a look at the workers tab. Here we can see basically the number of workers and their CPU and memory status and other important info. But now, of course, the Dask cluster doesn't have any workers. So we would like to scale it. We will do this with this button. So we choose 10 for this example. And now we can see here that there are some other Condor jobs that are sent to the HTCondor pool that contains the worker processes, of course. So as soon as they go running, we will see here the number of workers, the proper number of workers. So now they are running. So if we go here, we will see in some seconds the total number of workers. So here they are. Okay, now let's retrieve the analysis code that I pointed out in the slides, which is this one. We will do a very short, a very simple analysis. Which uses CMS Open Data, Monte Carlo, W plus Jets samples in order to get and doing a VBS-like analysis, but is only for example purposes. So here in the notebook, we do some basic imports and some basic definitions. I will come here later. Then here we we define the initialization function, as I mentioned before, declaring including the utils.h file, which contains all the necessary functions. Then we connect to the cluster, and we declare to RDataFrame the initialization function. We define the chain of files that we are going to analyze, and here we do the analysis itself. So first of all, we define the RDataFrame, then we define a dummy variation in order to show how it works. Basically, it is only scaling this variable. And then we do the selection of two jets, a muon, and a tau, basically, and then we compute the invariant mass of the four objects, and then we do the histograms. The histogram of this, we create the histogram of this variable. More specifically, we will create the histograms for all the variations. So we will have the nominal one, the variation up, and the variation down, and we will plot them. As you can see here, we will redo this, of course. We'll plot in the same canvas just for example purposes. So in order to be able to run this, we only have to set the correct scheduler port here. We only have to look at this number. So in this case, it's 21528. And then we have to choose the number of tasks to be sent to Dask. In this case, we have to choose, a good practice is to choose 3 to 5 times the number of workers that you have. So in this case, 50 is a good choice. So we launch the execution, and we go and see some useful tabs of the dashboard to look at the execution. So the progress one, the graph one, and the end processing. So let's go first with the graph one. The graph one shows basically the map reduce structure of the computation. So these are the mappers and the reducers, and then you get the results here, of course. Here instead you have the process, so you have the progress bar of the execution. You can monitor how many workers, how many tasks have been processed and are still to be processed. And finally, here you can have a look at how many tasks is running each worker, basically. And that's it. This is evolving, of course, and you can see here that the CPU usage of each worker. So as the computation goes on, memories are released, or results are kept in memory until they are released. And finally, we will hopefully see the computation over here, and we will get the results back in the notebook. Let's be patient for I think 10 seconds, more or less. And once the computation is over, we shouldn't see anything here, and we have to go back to the notebook to see the results. So three main reducers left. Here they are. So the computation is over, and then if we go here, we see that each color corresponds to a different variation, different varied histograms. And so we see the three histograms varied, and basically that's it. This is the workflow of the analysis code, the real analysis code that we use for the analysis. Coming back to the conclusions of this presentation, basically there are some lessons that we learned during all of this. Basically, we can say that the transition from legacy to distributed RDataFrame looks reasonably easy. Also thanks to the advanced features that were introduced recently, for example, the systematic variation. Another great added value is that you can do what you do locally, distributedly, with almost no effort, seamlessly. The same code works for both the scenarios. There are some issues with the debugging, meaning that there are occasional Dask task failures that are not well understood because there is no clear error pattern. Besides, if you want to take everything, to have everything under control, you have to monitor the resources in order to understand if there are possible bottlenecks or errors. Finally, we also use machine learning in our analysis. More specifically, we do inference. We do the inference with an external DNN model trained with TensorFlow. In order to use this external model, we need to go via ONNX files. So you have to move from TensorFlow format to ONNX format, and then use the TMVA SOFI engine. And basically, that's it. Thank you very much. If there are any questions, we are here. Thank you.
Hi, Tommaso and Vincenzo. Thanks very much for that presentation. It was really interesting. It's so great to see that scaling in practice. Okay. There are a couple of questions that we have. So the first one is from Michael, who's asking, how does this approach compare to using the Swan service at CERN? So I guess that's the infrastructure backend. Michael says, I'm not terribly familiar with it, but it seems designed for similar use cases.
I think Vincenzo can answer better than me. I think he's more experienced than me on Swan, but basically the interface is the same, of course. The resources, I don't know what resources are available on Swan. The great added value here is that you are integrating resources distributed geographically And so this is a solution that could be different, which means that the Dask scheduler is deployed on the resource that is distributed, is geographically distributed. I don't recall the resources that are available on Swan.
Yeah, exactly. So there are differences, let's say, at the infrastructure implementation level, but I would argue that it's not the point. I think the point here is providing this kind of interactive interfaces to users. The one that has been developed within the INFN group is valid, and it has a direct connection to grid resources that are managed by INFN. In general, the theme of analysis facilities is a quite popular one now. There are analysis facilities coming up and being developed and constructed. Swan is, let's say, one analysis facility. The important thing is that we or let's say the community can share the approaches, the interfaces, so that users can see, let's say, a homogeneous universe where they can run their analysis from some hardware to other hardware. I would say the actual implementation of the infrastructure is, let's say, secondary, as long as the software tools are able to cope with all the requirements that the users have. On that note, distributed RDataFrame already runs on Swan because it's available via the LCG releases. So if you have access to Swan, you want to try it out, feel free to do it. And if you want some help, you can also reach us on the Root forum or on the Mattermost channel. So I would say that's definitely something very, very flexible.
Another question, if I could, then we should close to go to the social time, right? Just one final one. How widely used is the workflow in CMS? Michael was asking.
Sorry, how wide?
How widely used is the workflow? So how are you getting along, attracting more people to try it out and see how it works for different analysis, maybe different workflows?
This is I think this is the first attempt to do this like this. Let's say I am aware of other analyses that tried to implement some part of the analysis in RDataFrame. Distributed RDataFrame is quite new, as if I recall well. So it's something that is being tried for the first times, I think, since 1 year and a half. Correct me if I'm wrong, but so there were some attempts, but this is, I think, the first time that we go end to end. So everything, every step of the analysis is. There are other tools that do this in CMS that are based on RDataFrame, but these features that we are using are brand new, let's say. So it's there were some attempts, and there are well-established tools that use RDataFrame, but all these new features are brand new, let's say. They were developed for this not only for this use case, but driven by this use case.
Yeah, so in that case, it's fantastic. Yeah, quite impressive actually. Thumbs up on this. So yeah.